In exercise 12.7, we're going to see a pattern that recurs in a lot of multi-step syntheses, and that is changing the carbon skeleton. There are two ways you can change the carbon skeleton. You can add more carbons, or you can take carbons away. We only know one way to add more carbons. That is to use a terminal alkyne. If you have a terminal alkyne, then, if you have a terminal alkyne and you treat it with sodium amide, that strong base, it will turn it into a nucleophile with a full negative charge. There's a hydrogen here, and the amide in sodium amide has a negative charge. And it can attack the hydrogen and push the leaving groups back on that carbon. That turns that carbon into a nucleophile. Gives it a full negative charge. So, if you treat a terminal alkyne, and it does have to be terminal, the alkyne has to be at the end of a carbon chain. If you treat that with a strong base like sodium amide, then it gets this negative charge and can act as a nucleophile. And you can make a new carbon-to-carbon bond by doing an SN2 reaction with that nucleophile. If, for example, you had, say, an ethyl group with a leaving group on it, chlorine, bromine, iodine, and the nucleophile attacks it, it could attack it and kick the leaving group off in an SN2 reaction, and you'll notice that what the result of that would be that you have this carbon here. This carbon on the end attached to, you'd have these two carbons here. You'd have those, and here let me just number them, 1 and 2. You'd have those attached to the carbon from the alkyne. So you can form a new carbon bond. You can add carbons onto the molecule by first adding sodium amide to a terminal alkyne, and second, adding some alkyl halide. Remember, any carbon chain is represented by a capital R, and any halogen is represented by a capital X. So that's one thing to keep in the back of your mind. If you see that the number of carbons gets bigger as you go from the left to the right of a reaction, then you know to do these two steps. And depending on how many carbons you want to add, you can make the R group there larger or smaller. So that's one thing you can do, one way to change a carbon skeleton. That's how you add carbons onto a skeleton. To take them off, the one way we've learned how to take them off is with ozonolysis. So for example, if you had a carbon here, and you did an ozonolysis on it, so remember for an alkene, it's O3 followed in a separate step by dimethyl sulfide. For an alkyne, the second step is water. What that does is it breaks this double bond and replaces it with double bonds to oxygen. Now, some of these molecules could be irrelevant, and notice if you just look at one half of it, it looks like you removed the carbon that was up here. So if you want to, if you look as you go from the left to the right of a reaction, and the number of carbons gets smaller, then you should think, maybe an ozonolysis. So those are two big principles. If the number of carbons gets bigger, think about this reaction here with a terminal alkyne. If the number of atoms gets smaller, think of this reaction here in ozonolysis. So with that sort of background, let's dive into these reactions for 12.7. So we notice we have 2 carbons in this molecule on the left. In the molecule on the right, we have 1, 2, 3, 4, 5. The fact that we have more carbons as we go from the left to the right is a sign that we're going to use sodium amide and an alkyl halide. So what we can do is take our molecule, and if we treat it with sodium amide, that will rip the hydrogen on here. There's a hydrogen here, a hydrogen here. If we just use one equivalent, then that will rip just one of the hydrogens off, because this is a strong base, so it'll steal that hydrogen, and the electrons in that bond to the hydrogen will become a lone pair that has a full negative charge. And so we have a carbon nucleophile. Okay, let's think about what alkyl halide we need to add in the second step here. So here we want to add 2 carbons. So we'll take that same group, those same 2 carbons, but instead of the alkyne at the end here, where the alkyne attached, we'll have a leaving group. And so this will do an SN2 reaction. It'll attack that carbon, kick the leaving group off, and we'll have that molecule there. So we'll have attached the terminal alkyne to the carbon that had the leaving group on it. Well, that's good. We have this part of the molecule. We just have to add one more carbon. So we have a hydrogen there right now. We can just do this process again to add more carbons. So we can add one equivalent of sodium amide, and that strong base will rip this hydrogen off. The electrons will snap back onto the carbon, and we'll have this molecule here. And then we just have to look at the carbon that we want to add. There's only one carbon we want to add. So we can take that one carbon, that group that's attached to the triple bond, and where it's attached to the triple bond, instead of the triple bond, we could have a halogen or a leaving group. So if we add that, our carbon nucleophile will attack this carbon, kick the leaving group off, and replace it. So the nucleophile replaces the leaving group, and we end up with our product. So overall, we looked at the reactants and the products. We noticed that the number of carbons was bigger. Anytime you increase the number of carbons, you always use sodium amide followed by an alkyl halide. Here we added carbons on both sides of the triple bond, and so we had to do that process twice. First, we used one equivalent of that strong base, sodium amide, that turned the carbon into a nucleophile, and then we added an alkyl halide. The alkyl halide had the same number of carbons as the chain that we wanted to add. So here it was bromoethane. That added one carbon chain on, but we still needed another carbon chain on. So we go through the same procedure again. We add one equivalent of sodium amide. That rips the second hydrogen off, and it turns it into a carbon nucleophile. And then we just need to treat it with another alkyl halide. The alkyl halide we use has the same number of carbons as the group that we want to add, so here just one. And where that carbon chain bonded to the triple bond, we instead have it bonding to a leaving group. So we add methyl bromide here. And those 4 steps were a sufficient synthesis to make this transformation happen. Okay, let's look at this one. Now, if you look at the number of carbons here, these both have the ring. So you have a 6-membered ring, a 6-membered ring, so that ties. But here, outside of the ring, we only have 1 carbon on the molecule on the left, and we have 1, 2, 3 carbons in the molecule on the right. So that's a sign that we have to use a terminal alkyne. Now, we don't have any type of alkyne here. Instead, what we have here is a leaving group. So this can act as the alkyl halide. That can act as the alkyl halide. We can take these 2 carbons that we want to add, right? Because this 1 is here, so we just need to add 2 and 3. We can take those 2 carbons that we want to add. We can add, we can treat it with 1 equivalent of that strong base sodium amide, and that will turn that into, because there are hydrogens here, so if you use 1 equivalent, one of the hydrogens will still be there, but on the other side, it'll get ripped off and its electrons will be a lone pair with a full negative charge. Once you make that, that can attack this alkyl halide and kick the leaving group off. And you could see how those two carbons then would add here. So you would have 2 and 3. So it's really just a matter of taking the acetylene, that's this ethyne molecule, treating that with sodium amide, one equivalent, and that's it. Now, the one thing about that is, if you do that, some sodium amide may rip off the hydrogen on the other side. So if you just want to be safe to do a water wash afterwards, to do a proton transfer to stabilize that, that might be a good idea. But otherwise, we looked at this molecule, we saw the number of carbons. When we looked at the product, we saw that the number of carbons increased. And so we knew we had to use a terminal alkyne, sodium amide, and an alkyl halide. The tricky thing here is they didn't give us the alkyne. Instead, they gave us the alkyl halide. So we had to add the alkyne ourselves and turned it into a nucleophile by adding sodium amide. Okay, let's try C. In C, you count the number of carbons up. In this long chain, we have 1, 2, 3, 4, 5, 6, 7, and then we just have an 8th one here. Now, I'm not numbering this as you would if you name it. I'm just numbering it to keep track of stuff, and that's why I can sort of make this jump here. That wouldn't be acceptable if you were naming it. Now, if we do the same thing, 1, 2, 3, 4, 5, 6, 7, oh my gosh, what happened to the 8th carbon? It turned into an oxygen. Here we have fewer carbons as we go from the left to the right than in this reaction. And so we saw if you try to get rid of carbons, the way to do it is with ozonolysis. And indeed, that's all you have to do here. You have an alkene, so the recipe for ozonolysis is going to be first O3 and second DMS, that's dimethyl sulfide. And what that'll do is it will split this bond. It'll cut that in half. And what you'll have is this molecule, that's what becomes of this half down here, and the oxygen gets added onto it, and then you have this other carbon on top that also gets a double bond to an oxygen on it. But they split apart, and this molecule goes on to live its own adventure. And so we took off and that's it, there's only those 2 steps here. So we removed a carbon by using ozonolysis. So in this video, we learned 2 big principles. If you want to add carbons to a carbon chain, then you use a terminal alkyne, sodium amide, to turn it into a nucleophile, and an alkyl halide for it to do an SN2 reaction with. And if you want to remove carbons from a carbon chain, you can do ozonolysis.